Uh, yeah, I was thinking to giving some more time because it's pretty bad weather because maybe somebody is getting late. But I guess probably we should get started. It's already 5 minutes past. Okay, so let's get started with today's lecture. And today is the second lecture about waiting line models. And for this week, it's not very tough as last week. So we're going to do a very light review of what we've done in last week. It's about what type of models we have, and so what theories is how to calculate by using the formulas. And also we're going to keep going on with a little bit more knowledge on the waiting line system, because in previous weeks we only consider one server or one employee serving for all the customers. But for today, we're going to considering what if we have more than one server and one employee serving all the customers. So let's get started. So, and this is the second week, so we are still in here, and from next week we're starting a new topic of inventory model. Okay, so let's do some pretty light review. So this is roughly all the equations, all the formulas we have in last week, and you've saw this and slides before. Let's go through that one by one. So we're gonna starting with queuing system or waiting line system, and by thinking about the probabilities that the whole system having 0 customers or 1 customers or 2 or 3 or 5 or infinite customers. So we're trying to find out the probability of having those number of customers. So, and fortunately, we can try to calculate the P0, which is the probability of having 0 customer, no customer in our whole system. That's basically equals to 1 minus rho. That means they're only determined by lambda and mu. And lambda is our arriving rate, so how many customers arriving in our shop or coffee shop. And mu is how many customers we can serve. So every certain period of time, usually we're using hour. So how many customers we can serve for 1 hour? How many customers arriving in our shop in 1 hour? And then later on, if we have the probability, apparently we can try to calculate expected number of the customers in our system. Because we have the number of customers, for example, 1, and we have the probability of having 1 customer in our system. So I try to calculate the whole probability of the all customers. So, and this mathematician, Eron, and he's trying to derive, so what if we linking the probability and the number of customers in our system? How to derive everything. So he derived and average number of the customers in our whole system. That's basically equals to rho divided by 1 minus rho. That's determined by utilization. And on the other hand, it's also only determined by arriving rate and the service rate. And at the same time, another mathematician, John Little, and he derived from another point of view. He thought maybe we should link the average number of customers in our system and the arriving rate and the time of the customer spend in the whole system. So when we see time, includes the time we are waiting there and the time with it. So 2 types of time, service and waiting. So in total, we call that W. So that's the total time we spend in the whole system. So, and John derived that the average number of the customer in our system, that basically equals to the time you spend, or one customer spend in the whole system, times how quickly we have basically the speed of the customer arriving, how quickly the customer could be arriving in here. So we have another relationship between L, that's the average number of customer, and the arriving rate and the total time of the customer spanning our whole system. So apparently we have L in the 2 equations. So we can link them together, and finally we can have the average time of a customer spent in the whole system, not only determined by the service rate and it's arriving rate and the service rate. You have a question, please.
Yeah, so to calculate the average, we use the other formula, right? Because
you mean the average time, or?
Yeah, do we use that formula? Or
so I don't want to say you have to use this formula or we need to use another formula. So this actually, all the formulas are the same because they derive by the same equations and of the source. Because this is one format, and also we have other formats in here, and so that's basically the same things. Yeah. So basically the same thing from the same source. So this is the source, and this is another source, and we can have this source, and we can have more equations there. So it really doesn't matter. So what formulas you want to use, but if you, for example, in a question, so basically whatever functions, whatever equations you're going to use, you should be having. If your calculation is correct, you should be having the same result. Same output. If you're using this, you have W, for example, 10. You will definitely have the same result by using the later on and those formulas in here. That should be the same. Okay, so and once we determine the average number of customers in our whole system, and we can also think about how to calculate the time. So the John Little's formula, L equals to W times lambda W times W, that also holds for the queue and the server respectively. Because in here, that's for the whole system. But we can also calculate the average number of customers in either the queue, that means how many customers are waiting there, and also we can calculate how many customers are being served. So LS, that's the customer being served. S represents for serve. And Q is the customers are waiting there in the queue. So we can calculate for the two things respectively. And so, but to do this, we have an assumption. The assumption is pretty simple. So we only consider two major components of the whole system. The components only including the queue and service. So we don't consider any other components. What if you want to have a talk with your friends? You want to picking up, you choose the best coffee. So we don't consider that. We consider if you go into the whole system and then you immediately waiting in a queue, and then when you finish the queue, and you are be served, and then you leave. So we only have two components in here. So that means the total time you spend in the whole system equals to the time you spend in the queue plus the time you spend to be served. And also the total number of customers in the whole system equals to the number in the queue and also the number in being served. So this is our assumption for the whole system, because we don't consider a very complicated and practical real scenario, but we consider slightly simpler situations in here. That's a little bit abstracted simulation. Okay. And if we want to calculate for the server and queue respectively, so the equation format is the same, but we have the subscript. So S is a representative for server, and Q is for the queue. So LS equals to lambda. Lambda is the same. That's all the arriving rate for the customers. And WS, that's definitely the time we spend in the service. So if we have this, I could try to calculate and to think about what is WS. So WS is the time one customer are served. So usually we should be knowing service rate. So that's basically how fast we can serve customers in a certain time period. For example, lambda equals to 10 and customer per hour. That means every hour we can serve on average 10 customers. So this is the speed. So if we know this, basically we can try to calculate and how many hours we need to serve one customer. So that equals to 1 divided by mu. So that's pretty much simple relationship between the time and the speed. So if we know the service rate, so we can easily calculate the time. And if we know the time, apparently we can try to calculate LS. That's the average number in the service. And so apparently if we having this and we substituting this relationship into this equation and lambda times WS, if WS is 1 divided by mu, we can find out LS that's basically equals to rho, that's the utilization of the whole system. So we have an interesting relationship between the number of customers in our service and the whole system utilization. That's basically the same, they have the same value, LS equals to rho. And so this is for the service. And we can also have, in parallel, we can also have the very similar relationship for the queue. So if people waiting in a queue, so we can try to calculating how many people on average are waiting in a queue. So that's represented by LQ. Q is abbreviation for queue. Lambda is the same, it's the arriving rate. And WQ is the average time Q. So that's we hope the same relationship of L, lambda, and W. But slightly different is, so how to find out the Q? Because in Q, we don't have any service. People just waiting there. But we have the assumption, so the total time equals to WQ plus WS. That's only the queue time and service time. So if we know the whole time, so we can easily calculating the time we're spending in the queue. So, and if we know the queue, if we know the time is spending in the queue, we can basically calculating the LQ by times the lambdas in here. This is one relationship. And another one is, what if you know the total number of customer in our whole system? And you can also calculate in LS, because we do this before, we've done this before. LS equals to rho. So if you know rho and if you know L, so we can basically having this relationship and find out LQ, so the average number of customer in the queue, that's basically could be derived by the utilization. So this is roughly all the equations we have in the last lecture. And what type of equations you have to remember for your final exams? That might be the top questions you want to ask. So you should definitely understand L equals to lambda times W. What is L? What is lambda? What is W? So you should know what does it mean for every symbols in here, and what is LS? What is WS? Because this is the same equation holds for the whole system and also for the queue and server respectively. But you should know every single symbols in here. So this is pretty simple relationship. But for most of the cases, the equations that you will need to calculate for whatever questions will be given in the exam for the queuing system. So, this is all we have in the last week. And not quite difficult, isn't it? So, okay. So in last week, we only basically consider one server. So, and this is the system we call MM1. And the last one, that means we only have one server. So when we're talking about the service rate, so what's the service rate? So service rate is mu. When we're talking about the service rate, because we only have one server, so the service rate is from the only one server. But what if we have more than one server? So that's the situation we are going to consider in today. So I think this is a pretty standard and pretty scenario you will see if you're going to a post office. So you are waiting in a line, but in a counter you have more than one employee waiting to serve you. So if you finish your waiting, so basically you could go to whatever counter and to be served. So in this example, the three employees, they are working in parallel. So every single employee might have a service rate, for example, mu, and he have a mu, he also has another mu, he has another mu. And three server working in parallel, so that means probably we can have, effectively, we can have a much more bigger service rate than just a mu because we have three servers. And So this is what we call multi-server model, 2 or more independent servers. So in most of the cases, we consider they are independent. But in practical, maybe they are not. So maybe they help each other and for one customer, so that's dependent relationship. We don't consider that. We consider all the employees are roughly independent to each other. That's more or less the practical cases in our daily life. And all the servers are working in parallel and serve a single waiting line. That's mostly the case. So if you go to the bank or coffee shop, you're waiting in the same line, but you have several employees waiting for you and waiting to serve you. So this is usually the case. One waiting line, parallel servers, and also first come, first serve. So that's usually the rule for our business. And also this is a pretty abstracted figure. So if you go into whatever shop or the service department, so you're waiting in a line. So we have a customer service stalls in here. We have 3 service employees in here. So we can waiting to be called. Once we are called, so we go into either of the server. Okay, that's the very simple case. And so if we have more than one server, we can roughly extend the previous weeks and figure. So if you are a customer, you arriving a shop, and then you immediately waiting in a queue. So because we can only consider one queue. So once you finish waiting in here, you're called. So you're going to either one of the server, maybe this or that. In here we call this MMS. Usually in this name, we're using S represents the multiple server, but actually in most of the calculations, we're using C and to represent the number of servers. So the first employee, the service rate might be mu, so we can easily calculating that. And the second one, we got another mu in parallel working there. And so on and so forth, we can have a lot of different mu's working in parallel. So apparently the total effective service rate is mu times C, and C is the number of servers. If we have 1, 2, 3, 4, 5, and to C, we have C servers and working in parallel. Every single server have a rate of mu, and so in total, the whole system, the service rate, effective service rate is going to be mu times C. And because this, I think it's quite straightforward because we have several things in parallel. So that's the total things we have. So let's think about if we have multiple servers in here. So the assumptions is basically the same. First come, first serve, because we only have a one queue. So, and we also assume the points and arrival, exponential service rate, and infinite populations. We are always having people coming in. So, and arrival rate is still lambda, and a service rate. When we say service rate, that's for only the every single server. For every single server, and we have a mu, and also we have a number of servers. So if this is a C, so that means effectively for the whole system, the service rate is C times mu. And so that's looks like this is the only change for our whole system. But actually, if you change this, so a lot of equations or the whole system's working scenario, working mechanism will be changed. So we're going to have a lot of quite different equations. So, so we immediately having those equations in here, but we're not trying to derive all of them because I think it's overcomplicated for us because it is basically math people's problem. Apparently, you don't have to remember those. And if you need to calculate all of those type of formulas and equations will be given. But you should know what does it mean for every single symbols in here. Let's go through it one by one. Okay, first of all the P and L and W, the meaning of that are the same as the single server system. When we say P0, so that's the probability having 0 customers in our whole system. So the probability having no customer in the whole system. And if you're looking at this, so the only reason we have such a complicated formula is that we have more than one server. So C is the number of servers in a whole system. If we have this, so basically we should do a lot of sum from 0 to C minus 1. If we have a 3 servers, C minus 1 is 2. So we are going to do for 0, 1, and 2. For every n, so we're going to calculate this factorial. And this is basically utilization with the power of n. So for 0, that's power of 0. For 1, it's power of n. And C is the number of customer. And this is the C factorial. And also this is the utilization with the power of and number of servers. Also, we need to calculate effectively, so what is the service rate? And service rate minus arriving rate. So this is how we're going to calculate the probability. We're going to show you one example later on. And apparently this is the Pn, that's the probability of having n customers. So in most of the cases, we're not going to ask you to calculate a probability. That's in most of the cases. So, but you still need to understand, so what does it mean if you have the equations in here? So apparently if we have n more than C, so in here, so that's roughly how we're going to calculating this. So n is the number of customers, and C is the number of the server. So think about if n smaller than C, that's probably a quite simple system because the number of customers is less than the number of servers. So for example, if we have 5 employees waiting there to serve all the customers, but in this hour, we only have 3 customers coming, that's pretty easy to serve because we don't even have the queue because that's pretty easy because everybody should go to the counter immediately without waiting any time because we have more employees there serving the customers. So we have quite different equations for calculating the probability of having n customers. So this is for the case we have more customers than the server, and this is for the case we have less n customers than the server. And L, so the meaning is still the same, so that's average customers in the whole system. So, and W, that's the average time for customer span in the whole system. And so if you're looking at this is roughly pretty much similar with before because we have lambda times mu, but in here, lambda divided by mu with the power of the number of servers with a C. And in here, we need to calculate the C minus 1 factorial and also the effective service rate and minus the lambda. That's basically the arriving rate. So with a square and times a P0. And P0, usually for most of the cases, P0 will be given. But what if for some cases it was not given, so this is the equation. The equation will be given to calculate this. And if you're having the total number, average number of customers in the whole system, so you still need the same equation to calculate. So on average, so how long you're going to spend in the whole system, because that's only using L, the number of customer, divided by the arriving rate. Then you will have arriving times you are spent in the whole system. Okay, and so also we're going to have quite different equations, maybe not very different, because for this equation, that's basically the same. So the average number of customers in the queue, LQ, so the meaning of the symbols are the same. So that equals to the total average number of customers in the whole system minus the number of customers in what? In the service. So in service, that's basically equals to mu divided by lambda divided by mu. So that's equals to the utilization. And we've done this before. And also, if you have LQs in here, so you could also calculating an average time of the customer in the queue. So that's W minus 1 divided by mu. And this is roughly the relationship. And also for the probability of customer waiting for the service, that's roughly the pretty much similar things and with before. But For all of those equations, all you need is you need to understand for each symbol what does it mean. And once those formulas were given to you, and you should know how to use the formulas to calculate. So usually the questions will be like a story. So you are looking at a story and figure out what is the arriving rate, what is the service rate, how many servers we have, and if we only have one server, cool. That means C equals to 1. What if we have multiple servers? So that basically means we're going to using those equations. Yeah, please.
Which is the difference of a letter having an exclamation sign and without? For example, in the formula, in the other,
Mm-hmm.
The N, the first N has an exclamation sign, or anywhere there's an exclamation sign, and then, no, the C, for example.
Yeah, you mean a factorial?
Oh, okay.
Yeah. You don't know how to calculate a factorial, or so if you have an n factorial, that means you have to multiply from 1, 2, 3, 4, 5, and to n. That's how we're going to calculate your factorial. Yeah. Okay, so I think a better way is to use an example. Okay, so let's take a look of this example. So this is a pretty simple example. It just show how we're going to using the formulas. So if we have a shop and a customer arriving rate is lambda equals to 10 customer per hour, that's pretty standard. And the service rate is mu equals to 4 customer per hour. So looks like the service rate is pretty low, but we have C equals to 3 counters for serving the whole customers. So that means we have a multiple server system. So, and if you think about this, mu equals to 4 and C equals to 3, so effectively, so the service rate should be 4 times 3, should be 12 customers per hour. And we have arriving rate 10 customer per hour. So that should be a stable system because we have effective service rate and larger than the arriving rate. Okay, so and first, what if we hope to calculating for based on the given conditions, what is the probability of having 0 customers and no customer in our whole system? So, and this is the equation. Okay, and first of all, C in here. So C is the number of servers. In this question, we have C equals to 3. So that means we should calculating for the sum. So this is a sum symbol from n equals to 0 to C minus 1, that's 2. So we should calculating for n equals to 0 and 1 and 2, 3 situations and 3 cases. So if n equal to 0, so 0 factorial, that's equals to 1. And so what is the lambda? Lambda apparently is 10. What is mu? Mu is 4. So when we hear in the equations, so mu is just the service rate for single server. So mu is just a mu. So do not try to using the effective mu's in here. So when we say mu, that's just a service rate for a single server. So, and then additionally, we should know how many servers we have. In here, we have 3 servers, but every server, the service rate is mu, it's 4 customer per hour. So in here, mu is 4 customer per hour, and the arriving rate is 10. So for the first case, n equal to 0, and the second case, n equal to 1. So 1 divided by 1 factorial, and n factorial, that's basically, and 1's factorial is basically 1. And with n equals to 1, so 10 divided by 4. And then we're going to move to the next one is the n equals to 2. When n equals to 2, we need to calculate the factorial. That's equals to 1 times 2. That's basically 2. And when n equals to 2, we have a power of 2's in here. And plus, the next part is C factorial. So C factorial is 3. C is 3. 3 factorial equals to 1 times 2 times 3. So, and lambda is also 10, mu is 4, because it's the service rate, with the power of 3, because the power of C equals to 3. And the next part is, so C times mu. C is the 3 counters, and mu is the 4 customers per hour. And so also we have a 3 times the 4 minus lambda, that's the arriving rate. So this is pretty big equations, and we should calculate them one by one. And finally, we can calculate the probability of no customers. And so if we have this, so apparently we don't need to, maybe it's not, we don't need to calculate the probability of 0 customers for every single questions, but this is the case what if we need to calculate. And if we have a p-zeros in here, so we can calculate the L, that's basically the total average number of customers in our system. So this is the equation, so let's take a look. Lambda, that's the arriving rate, and mu is the service rate, and apparently lambda divided by mu, that's the utilization with the power of C. C is the number of servers. In here it's a 3. And C minus 1 factorial, and C is 3. 3 minus 1 is 2. 2 factorial is 1 times 2. And C times mu, and minus lambda with the power of 2, and times the p0, and p0, we just calculated p0s in here, and also plus the lambda arriving rate divided by the mu, the service rate. So and if we're substituting all the numbers in here, that shouldn't be quite hard to calculate. So, okay. So once we got L is a 6 customer on average in the whole system. So we can basically try to calculate the W. That's the total time we spend in the whole system. So we're using the same equations. So L equals to lambda times W. So W equals to L divided by the lambda. So lambda is, so what is lambda? 10. 10's in here. So we substituting 10, and L is a 6. So apparently 6 divided by 10, we have 0.6 hour on average for one customer stay in the whole system. That including the waiting system in the queue and also system in the counter. Okay, so if we have calculating all of those, we can also keep going on. So we can have LQ equals to basically the L, we just got L, that's a 6. And L minus LS, that's basically the utilization, and without considering multiple servers. So that's 10 is our lambda arriving rate divided by 4, that's the service rate for single server service rate. And then we can get so 3.5 customers on average waiting to be served. Okay, so if you're having this, so basically we can calculate WQ because we know LQ. So that's the number of customer divided by the lambda. Lambda is in here is 10, so arriving rate. So using L divided by lambda, because L equals to W times lambda, that's always be the equation we have. So we can have the times we waiting in the line per customer. And so we got this, so we can try to calculate the probability of W. So where's the probability of W? Using these equations. So we can substituting C and mu and lambda and also P0. That's the probability of zeros in our whole system. Okay, so this is how we're gonna using those equations and for calculating if we have multiple servers. So C. Most of the cases, because calculating P0 is pretty complicated, for most of the cases we don't need to calculate. So I'm gonna show you some of the real examples later on. So this is just a small summary for this part. So the Little's law, L, the number of customer equals to the arriving rate times the time. So W, the average time you're spending in the whole system. And so this is I can say this is a golden formula, so you're going to have to understand and remember, because this is a very important relationship for the whole system. And regardless, just single server or multiple servers you have, so you're always having these relationships. And so if we have this, so basically this relationship holds for the whole system or queue or the service respectively. So you can try to calculate the average number of customer and also average time. So basically those are two important factors and two important things we need to figure out for this problem. So average number of customer and how long you're gonna wait for waiting or for the service. So, okay, and let's try to keep going on from the last week's example, because in last week, and we finished by doing part of this example, and this is the real example from the last year's final exam paper. So, and this is a waiting line system. And in last week, we tried to calculate the first question, part of a first question. So, so the first question is about what is the arrival rate. It's pretty simple. What is the arrival rate, service rate, inter-arrival time, service time, and utilization with 3 employees? Is the system stable or not? That's roughly the basic things. So if you're looking at whole and story, so basically this is a story of cargo and Argo and Sea Argo. So you're gonna go into the service house and you're waiting there and picking your things, picking basically, and I don't know, so whatever goods from employees. So, and this is a quite typical waiting line system, and they say the shop have trying to employ 3 peoples, and a single employee can serve 15 customer per hour. So apparently, so this is for single server service rate. Every hour we serve 15 customer. And a rate of arriving is roughly 40 per hour on typical day. So that's basically an average arriving rate, 40 people per hour. So this is 3 important conditions we know. So based on this, so what is the arrival rate? So apparently we already given in here is 40, arrival is 40 customer per hour. We've done this in last week. And what is the service rate? Apparently we have the service rate for a single employee, single server. That's 15 customer per hour. Okay, and inter-arrival. So how to do inter-arrival? That's pretty simple because we know the arrival rate, that's how many customers arriving in an hour. So, and inter-arrival is how many hours we can expect 1 customer. So just 1 divided by the arrival rate, we got 0.0225 hour. So they're roughly 1.5 minutes. You can answer hour per customer or minutes per customer. So that's basically all fine, but for hours, it's maybe not very easy to understand. So it's pretty okay to convert. You don't convert, that's fine. So you can answer either 0.025 or 1.5 minutes per customer. But the units is pretty important. You cannot just write 1.5 in here. So we don't know it's minutes per customer or hours or whatever. And the next time is, the next question is the service time. If we know the service rate, so we should definitely know the service time for 1 single customer. So 1 divided by the service rate is 0.0667. That's pretty hard to understand. If we convert it to minutes, that's roughly 4 minutes per customer. So every customer, we need 4 minutes to serve him. Okay, and then is the utilization with 3 employees. So the question is very clear. So we need to calculate the utilization with 3 employees. So that means we need to find out what is the effective total and service rate. So apparently, for a single employee is a 15. We have 3 employees. So 15 times 3, that's 45. That's the effective service rate. So lambda is arriving rate, 40 divided by 45. So roughly we got 88.9%. And so this is the utilization with 3 employees in here. And apparently this is smaller than 1, so the whole system is stable. Okay, so this is for the first question. And So I want to just put this again, because this is for the first question. When we calculate the utilization with 3 employees, so we know this is a multiple server and question. So C equals to 3. So we can calculate the utilization of a 3 with the 40 divided by 15. That's the service rate for single server times the number of servers. It's a 3. We got the service rate. Okay, this is for the first question. And then let's take a look for the second question. Okay, so how many customers on average in a waiting system? How many customers in a queue? How many customers are dealt by the employees? So this is a pretty typical question. So on average, how many customers in the system and queue and the service? And so that's how we're going to calculate the number of customers. So we definitely need some formulas. And apparently, this is a multi-service system. We need pretty complicated equations there. And those are in here, those are equations and given in the exam paper. So this is the only equations given in the exam paper. So you have to figure out how we're going to using those given equations and to calculate this question. So let's take a look. So what is the equations given in the final exam paper? So the first one, L equals to lambda times W. That's pretty simple. That's just the basic functions. And so the number of customer equals to the arriving rate times the time. And also LQ equals to lambda times WQ. So this is for the queue. And also this is for the service. So this the 3 equations in here, this is pretty standard and very basic things. And then we have U, and U is the utilization. And also we can call that rho or U as the same. And that equals to lambda divided by C times mu. Apparently this is for the effective service rate. And then we have LQ equals to a lot of calculation times P0. And what is P0? Probability of no customers. Okay. And so apparently we have here a hint. Using MMC queuing model, assuming P0 is 0.028. So apparently we don't have to calculate P0. So they are given. And now, what is LQ? So we got a question of LQ. What is LQ? The average customer in the queue. Yeah. Okay. So this is something you have to know. If you got LQs in here, you don't know what is LQ, that's your problem. Okay. So if you know, okay, fine, we got LQ, that's the average number of customer in a queue. And this is apparently one of the questions. So what is the question? So how many customers are in the queue? So that's basically how we're going to calculate. So let's take a look on this equation. So P0 and given, cool. And lambda, what is lambda? And 40, cool. What is mu? 15. And C, what is C? With the power of C, C is 3. We got 3 servers. And so in here we have C minus 1 factorial. Apparently this C minus 1 is 2. 2 factorial is just 2. That's pretty simple. And we got C times mu, that's the effective service rate, minus lambda, arriving rate with the power of 2. Is that simple to calculate? I believe so. So if you know what is Q and what is LQ, and you will know how to calculating the average number of customer in a queue by using this. And apparently C equals to 3 and P0 are given, so that's the assumption. What if we have the probability of this? And okay, if you have LQ, then you could think about, is it possible to calculate some more? Because we need to calculate also the LS and the L, the total L. So we have LQs in here. So apparently we have another equations in here. L equals to LQ plus, what is this? This is actually LS. LS equals to the utilization, but it's not this utilization. So this is the effective utilization. So we only consider this. Okay, so LQ, we just done this. So this is a 6.3716. And lambda, apparently is pretty simple. We have 40, and what is mu? Mu is 15. So we substituting everything, we got roughly 9.03 customers in our whole system. Okay, if you got L and LQ, so apparently you can immediately calculate what is LS, so how many customers and in service on average. So that's basically the second question. So, and if you're going back, so I think you can see the second question have 8 marks. The first one is 9 marks, so apparently it's pretty simple to have 17 marks immediately. And okay, now let's move into the last question. So we know how many customers on average in the system, queue, and service. Now the next one will be time. So how long do customers have to wait in a queue, and how long average waiting in the whole queue system? And would the average waiting time be less than 10 minutes when 3 people are employed? So this is just pretty simple. How we're gonna calculating the average and waiting time? Because we know LQ, which is calculated LQ, and in last questions, and then we can calculate WQ, that's the time, divided by lambda, that's the 40. So roughly we got this number that's not easy to understand, so we can convert it to minutes, 9.55 minutes. Okay, so is it less than 10? So apparently it's less than 10. And because we calculate this with 3 employees, that's the reason. The reason is we calculate LQ by using this equation, because in this equation we consider 3 counters, 3 employees serving this. So, and this WQ is the time when we consider 3 employees. Okay, and so how long are customers on average in the queuing system? When we see the whole queuing system, that including everything, service and queue. So because we have L and we have lambda, and that's pretty easy to calculate everything using here, roughly, and less than 14 minutes in total. Okay, cool. That's basically how we're going to calculating using all of those equations. And so I think from this example, it could be quite easy to know. So what if those equations are given? What you have to figure out what is arriving rate, what is service rate, how many counters we have, how many employees, and how many servers we have. And so what equations are given. So if we only have LQ, that's fine. We're going to using LQ to calculate. So you should know what is LQ and how. If you have LQ, you should have the understanding to derive all the other numbers and values from the LQ. Okay, so let's try to enhance your understanding. So we're going to doing slightly more examples, because this is all about a waiting line system. Not necessarily to be a multi-server, but either single server or multi-server. So every time when you see a question, you should read the question, read the story, and figure out, is it a single server problem or multi-server problem? So this is your understanding. So let's take a look. So I think this is one of the questions in the problems? Yeah, I guess so. Okay, so let's take a look. So this is, I think it's pretty simple and straightforward question. So what if we got one person and he is trying to sell ticket for a football game? Okay, and now we mentioned only one person who is selling ticket. So apparently this is one server, single server problem, because we only have one person selling ticket. And ticket seller can serve an average 12 customer per hour, and on average 10 customer arriving to purchase each hour. So apparently we can immediately know 2 things. So what is this service rate, and what is this arriving rate? And it looks like that's going to be a stable system, because we can serve more than the customer arriving. And single server, because we only have one person, that's apparently the condition. And so it's C equals to 1. And apparently we have 10 customer arriving per hour. And we know this is one of the condition. Another one is 12 customer could be served per hour. Okay, this is all we know. And if we know this, apparently we can calculate the utilization using the arriving rate divided by the service rate. So, and it's pretty much stable because less than 100%. And so if we're looking at this, the portion of time the ticket setter is busy. So, and this is one format of the question. The portion of the time. So apparently this is 88.3% portion of the time, and the ticket setter is busy. Another format is the portion of time the ticket setter is not busy or idle. So that apparently we should using 1 minus 88.3%. That's the percentage of the time he's idle there on average. Okay, this is the two format of the questions, but roughly the same things. So if we hope to calculate the average time the buyer must wait, so this is the time we're spending in the queue. So we cannot directly calculating that, but we can calculating, so we know mu, so this is the service rate, we can probably know the service time. And if we know the service time, we can also calculating basically the L, so using rho divided by 1 minus rho. So this is one of the basic equations. And we know 5 customer and on average. So we can, if we know L and we know lambda, so we can know roughly we need 30 minutes in the whole system. And if we know 30 minutes in the whole system and 5 minutes in the service, roughly we can know, so 25 minutes for waiting in a queue to buy a ticket. So this is an average time the buyer have to wait for the whole system to be served. Okay, so this is roughly a pretty simple and straightforward questions. Yeah, please. Yeah, take your time. Sorry?
Which formulas will they give us?
Which formula will be given? So the answer for this question is, so you were definitely formulas and could be, so for, if you're only using the formulas in the final exam, you are definitely solve the problem, but maybe not by the way you're thinking about, but you have to find out a way. So we can make sure you can solve the problem by the given formulas, but you have to figure out how to do that. For example, if you want to calculate L by using this, but you forget this, and those equations are not given, but you definitely find another way to calculate L, because we have plenty of ways. Maybe you have to calculate it by rho, but maybe by some other things. But you'll definitely find a way by using the given formulas there. So now how to find a way, that's your understanding. You should know the relationships, because all of those equations are roughly related to each other. They are, if you do some manipulations of the equations, they are the same, actually. Okay. So that's one question. And let's take another look at another one. And this is not very typical question. And because we don't actually have a coffee shop, and we don't have any house, or we don't even have a waiting line there, because this is something about the planes. What if you have an airport, a pretty small airport, and serves for light planes? So, and it has a single runway, one air traffic controller to land the plane. So apparently this is not a very typical waiting line, but think about this is abstractively, and this is basically the same. If you think about a mathematical model behind the question, behind the business story. So if a plane arrives at an airport, and the plane has to wait for some times until it receives the signal from the airplane, basically the controller, traffic controller, and tell him, okay, now you can land. I can tell you how to land. So what is your angle? What is your speed? So maybe you're too quick, too slow. And so this is the service. And before the plane could be served to landing, and the plane has to wait for some time, going circle and in the air above the airplane, above the airport. So this is, if you think about that, that's roughly the same things. A plane arrived at the airport, and the plane has to wait for some time. But for all the planes, they cannot standing there in a queue, but they are logically waiting there in a queue. So you are the first one arriving, and here's the second one, and that's the third one. They are all going circle in the air and waiting, so as a queue, but not physically looks like a queue, but actually they are waiting in a queue and waiting to be served. And so we know it takes an airplane 12 minutes to land, and not including the time waiting to be landed. So think about 12 minutes. That's basically the landing time. So during the time, you will need a service from the air traffic controller. So the air traffic controller serves you and to landing on the airport. So that's basically the service process. So you need 12 minutes to finish the service. That's basically the service time. And plane arrive at airport at a rate of 4 per hour. So this is apparently the arriving rate. So every 4 hours, we are expecting 4 planes arriving into our airport. And for every plane, he might need to wait for some time and to be served to landing. So this is actually a waiting line system, but we don't physically see a line or waiting line there, but that roughly the mathematical behind it is the same. Okay, now we need to calculate. So average number of plane was stacked up waiting the air to land and average time. And so basically things, average number and average time. So 2 types of things we need to calculate. Okay, and the last question is a little bit more like a business story. So if an air controller can land a plane maximum 45 minutes out of every hour, maybe this is regulation. So there must be 15 minutes idle for a rest. So okay, if we have the regulation, will the airport have to hire an extra controller? So we're gonna need to calculate something. So see, is it possible for a controller to working for 45 minutes and have a 15 minutes to have an idle time to rest? Okay, so first of all, and let's see, what do we have? So we have a single runway and a single travel controller. This is a single server and takes an airplane 12 minutes to land, not including the waiting time to land. So apparently this is a service time. But this is not service rate, it's a service time. And the plane arrived at the airport at a rate of 4 per hour. So apparently this is it's not customer, but 4 planes. But plane could be one type of a customer, so 4 customer per hour. So this is the arriving rate. So what do we have? C equals to 1 single server problem, and lambda 4 planes per hour. And waiting time, so this is 12 minutes per plane. So that roughly is 0.2 hour per plane. So okay, so if we know this is the time. So is it possible to know the service? The service rate. So apparently we could easily calculate 1 divided by 0.2. That's 5 plane per hour. We can serve 5 plane per hour. We only have 5 plane arriving, so that should be okay. It's a stable system. Okay, and so again, so we try to using rho divided by 1 minus rho to find out the total number of the customers, and in this case is the plane in our whole system. So we can have 4 planes, and also if we know the service time, apparently service time is a given condition, 0.2, and also we know the lambda. Lambda is arriving rate, so we can calculate the average plane in the whole service, and this is for the service. Okay, so if we know the service and also we know the L, the total planes, so basically we can calculate L minus LS. That's roughly 3.2 planes on average plane in a queue waiting to be landed. And because we know LQ, apparently you can easily calculating by using LQ divided by lambda. That's the time, average time waiting in a queue. That's 0.8 hours, roughly 48 minutes. Okay, and apparently if we know the time to waiting and also the time of landing, the service, so we should know. So on average, so from notification to landing to finish landing, so that's the whole time, the average total time of playing, we're going to stay in the queuing system. And so, what about the last one? So if we know, because this is a single server problem, if we know the arriving rate and the service rate is 5, so we can calculating the utilization. It's 80%. Okay, and now the regulation is if we're working for 45 minutes, we need to have an idle time of 15 minutes. That's roughly the 3/4 of 1 hour. That's basically 75% of the standard. So this is a standard. So apparently we have 80% of the utilization. That's higher than the standard. So that means we cannot let the controller rest for 15 minutes if he's working for 45 minutes. So we might probably have to hire more controllers for this problem. So we can simply consider just the utilization and the standard things. So compare the two numbers, we find out fine. It's not possible to let him rest for 1/4 of 1 hour time. Okay, so and this is also a single and server problem. So and I think for this problem, the crucial thing is you have to think about this is not very typical waiting line. We don't have a line there, but basically the logic behind the story is the same. So if you figure out the server, so the single runway and a single controller, single server, and 12 minutes to land. So that's basically the service time because we need a controller to serve us and also the arriving rate. So if you figure out those crucial symbols and crucial and variables, you should be able to calculating those. Okay, let's move on to another question. So this is a little bit more like our final exam questions and the type of final exam questions. So what if we have a customer arriving in a bank? So that's apparently a very typical waiting line system and waiting a queue to be called to a counter for their business. And the general manager, experienced manager, knows the customer arrives at a rate of 25 per hour on average. So apparently we know this is the arriving rate and a single counter can serve 10 customers per hour on average. So when we see single server, so we know, okay, so this is the service rate for just one server, one employee. The bank wants to make sure the customer will not wait longer than 6 minutes. So the shops try to open 3 counters. Okay, so that's pretty clear. So we have several conditions. 25 per hour, that's arriving. 10 customer per hour, that's service rate for single server. And 3 counters, that means we have 3 servers. So this is apparently something we can write it down. C equals to 3 servers. Arriving rate, 25 customer per hour. Service rate, 10 customer per hour. That's basically the same things. And the first question, also pretty simple. Arrival rate, we got this here. Service rate, we got this here. So now what is inter-arrival time, service time? Apparently we should try to calculate 1 divided by and lambda 1 divided by mu. So we can calculate inter-arrival time and service time. That's pretty simple things. And what is utilization with 3 counters is system stable. So that's pretty simple because effective utilization is the arrival rate divided by the counter, number of counter times the service rate. So 83, that should be fine because it's less than 100%. Okay, and now the next one, we're going to move into the customer. How many customers on average in a waiting line system? So for this type of a question, apparently we should be having these equations and LQ given. So if we have this LQ, we should know, so this is the average number of customers in our queue. So, and we know the arriving rate, service rate, and number of the surveys, and also P0. So for most of cases, we forget to mention, so the P0 is also given, because we are assume P0 is a 0.028, so that should be a variable given there, but I forget to put it in here, so I forget that. So P0 should be given, somewhere in the whole question. So it should maybe 0.028 or some other values, but anyway, that's one of the condition you know. And so if you're substituting this and with P0, and you should find out LQ, so the customer in the queue on average. So if you know this, and apparently you should know how to find out the total and customer by using LQ plus this is the utilization actually, 25 divided by 10. And this is the total customers in the whole system. And apparently you should easily substituting from L by LQ, so you will know the average customers in the service, 2.5 customer in the service. And okay, so this is for the number of customer. And after that, we're gonna determine the waiting time. So, because apparently the first one is pretty simple. We know LQ, so we can easily calculating the time in the queue. So by using LQ divided by lambda, lambda is 25. Okay, and when we know the WQ, so it's pretty easy to find out the total time because we already know the service time because it's a 6 minutes per customer, and we plus 6 minutes and the average time in a queue, so that's the total time. So in a queue system. Okay, so basically that's everything. Is that simple? Yeah, I can see some people are nodding. Okay, yeah, it is simple. So I think for this question, so for this type of a question, what I can say is you should make sure you understand what is L, what is lambda, what is W. So I repeated this for many times. So this is the basic equations. And this equation applies for the whole system and service and queue respectively. So everywhere. And you should be very clear about what is arriving rate, what relationship between arriving rate and inter-arrival time, and what is service rate and the service time. That's also pretty simple. And how to find out the utilization and how to find out the effective utilization if we have more than one server there. And if you know those relationships of the equations, and if you understand what is LQ, LS, WQ, WS, the four crucial variables, and by using the given equations, you should be able to calculating all of those. Yeah, okay. I think, and the examples in this lecture are pretty crucial for preparing basically your exams, and also to give you some understanding, more deep understanding on what is waiting line system. Okay, so that's basically everything for today. And don't forget the lab. So we're gonna try to do a very interesting business problems in the lab in today and tomorrow. Okay, thank you guys.